Hello friend, welcome to my channel GATE and ESE aspirants. In the last lecture we have discussed four properties of fluid. Now in this lecture we will discuss remaining properties of fluid. Start from vapor pressure. Let us consider a closed container which is partially filled with liquid. The molecules on the surface of liquid are in highly excited state, and this molecule by taking energy from the below molecule and they get evaporated. The air above the liquid can absorb these vapor molecules only up to saturation. Once the saturation reached, the number of molecules leaving the surface of liquid on evaporation becomes equal to the number of molecules condensed back to the surface. And such a condition is known as saturation or equilibrium condition. The pressure exerted by vapor molecules over a surface of liquid under saturation condition at a given temperature is known as saturated vapor pressure or simple vapor pressure. With increase in temperature, vapor pressure increases. More volatile fluid are having higher vapor pressure. Example like petrol. Mercury is having least vapor pressure because of strong cohesive bond. Due to this, mercury is used as a manometric fluid in pressure measurement. Cavitation. Formation of vapor bubbles within a liquid at low pressure region that occurs in place where the liquid has been accelerated to high velocities, as in the operation of centrifugal pumps, water turbines, and marine propeller, etc. Now let's see the picture. Whenever in a flowing fluid, the pressure of the flowing fluid becomes less than the saturated vapor pressure, boiling will start and bubbles are formed. When these bubbles move to the high pressure region, the pressure fluid collapses these bubbles and strike with the wall. And this wall may lead to wear and tear and may be bursting, and such a phenomena is known as cavitation. In the converging section, velocity is increasing and pressure is decreases. And in divergent section, velocity is decreases and pressure is increases. And minimum pressure at the throat. Cavitation is a low pressure phenomena. To avoid cavitation, design must be done in such a manner the pressure of flowing fluid becomes more than the saturated vapor pressure. If minimum pressure is greater than vapor pressure, then the flow is normal flow. If minimum pressure is less than the vapor pressure, then the boiling will start and bubbles are formed. And cavitation is present. Now sixth property is viscosity. Viscosity is defined as the internal resistance offered by one layer of fluid to the adjacent layer. In the figure, we can see that the fixed surface is having velocity 0 and it is increases gradually. It is because of viscosity. Rate of deformation is equal to the velocity gradient. d theta by dt is equal to the du by dy. In solid, we can say stress is proportional to strain, but in case of fluid, shear stress is proportional to rate of shear strain. So tau is directly proportional to d theta by dt. So tau is equal to say mu d theta by dt. So tau is equal to say mu du by dy. Here tau is equal to say shear stress and mu is equal to say dynamic viscosity and du by dy is equal to say velocity gradient. Expression for shear force is given by F is equal to say mu a v by y. Here mu is dynamic viscosity, A is area, V is velocity of fluid and Y is the vertical distance. Newton's law of viscosity. All those fluid are Newtonian fluid which follow the relation shear stress is directly proportional to rate of shear strain. Here tau is directly proportional to d theta by dt. So tau is equal to say mu d theta by dt. So we earlier know d theta by dt is equal to say du by dy. So the final expression is tau is equal to say mu du by dy. Now plot a graph between shear stress and rate of shear strain. Here we can see the curve of oil, water and air. Important point. First, in case of liquid, the main reason of viscosity is molecular bonding, whereas in case of gases, it is molecular momentum transfer or collision. Second, viscosity basically represents the easiness of flow. More the viscosity, more is the resistance, and it is difficult to flow. Viscosity is also known as coefficient of viscosity or absolute viscosity or dynamic viscosity. Its dimension is ml the power minus 1 and t the power minus 1. Variation of viscosity with pressure. Viscosity varies negligible with low to moderate pressure. Hence, effect of pressure on viscosity is not important. Variation of viscosity with temperature. In case of liquid with increase in temperature, viscosity decreases due to cohesive bonding. In case of gas with increase in temperature, viscosity increases due to increase in molecular collision. Let us plot a graph between viscosity and temperature for liquid and gas. In case of liquid, viscosity decreases with increase in temperature, whereas in case of gas, it increases with increase in temperature. Let us combine these two graphs. Here we can clearly see the variation of liquid and gas. Kinematic viscosity nu. It is defined as the ratio of dynamic viscosity to its density. So nu is equal to say mu by rho. Its unit is meter square per second. Its dimension is L the power 2 and T the power minus 1. In the dimension, we did not see the mass term. That's why it is called as kinematics. Important points. Dynamic viscosity shows the resistance to motion, whereas kinematic viscosity shows resistance to molecular momentum transfer or collision. Units of viscosity. Dynamic viscosity SI unit is Newton second per meter square and its CGS unit is poise. So 1 Newton second per meter square is equal to say 10 poise. Kinematic viscosity SI unit is meter square per second and CGS unit is Stokes. So 1 meter square per second is equal to say 10 to the power 4 Stokes. Variation of viscosity with increase in temperature. In case of liquid, dynamic viscosity decreases and kinematic viscosity decreases, whereas in case of gas, dynamic viscosity increases and kinematic viscosity increases with faster rate. Newtonian fluid, which obey the Newton's law of viscosity, and non-Newtonian fluid, which does not obey the Newton's law of viscosity. Fluid can be defined as Newtonian and non-Newtonian fluid. Non-Newtonian fluid further divided into two categories, time-dependent and time-independent. In time-dependent, dilatant, pseudoplastic, and Bingham plastic. Time-independent, thixotropic, and rheopactic. In the graph between tau and du by dy, we can see ideal fluid, dilatant, Newtonian, pseudoplastic, Bingham plastic, and ideal solid. Fluid example. Dilatant is shear thickening fluid. The example are sugar solution in water, starch solution, and quicksand, etc. Pseudoplastic shear thinning fluid. Its example is blood and milk, etc. Bingham plastic, toothpaste, gel, lipstick, etc. Thixotropic fluid, ink and paint. Rheopactic, gypsum in water. Now, seventh property is surface tension. Let us consider a molecule below the free surface. This molecule under the action of balanced cohesive forces from all the sides, and hence this molecule is under the equilibrium. Let us consider a molecule on the free surface of liquid. This molecule under the action of unbalanced cohesive force, and it experiences a net downward pull. This molecule is under a stressed condition. All the molecules on the surface are under stressed condition, and their appearance will create the member of stressed molecule over the surface that can bear a small load, and such a property is known as surface tension. The main reason of surface tension is unbalanced cohesive force. With increase in temperature, the surface tension is decreases because cohesion between the molecules is decreases and unbalanced cohesive force is decreases, and hence surface tension is decreases. It is defined as the force per unit length and its unit is Newton per meter. Its dimension is m t the power minus 2. Surface tension of water is 0.0732 Newton per meter at 20 degrees Celsius. Pressure inside the liquid drop. So gauge pressure is equal to say 4 sigma by D, and pressure inside a soap bubble. So gauge pressure is equal to say 8 sigma by D, and pressure inside a liquid jet. So gauge pressure is equal to say 2 sigma by D. Eighth property is capillarity. Capillarity is defined as the rise or fall of liquid when a small diameter glass tube is inserted in it. Capillarity rise is due to adhesion and capillary fall is due to cohesion. For pure water in contact with air in a clean glass tube, the capillary rise takes place with theta is equal to 0. Mercury causes capillary depression with an angle of contact of about 130 degree in clean glass in contact with air. Expression for capillary rise. So H is equal to say 4 sigma cos theta by rho gt. Expression for capillary fall. H is equal to say minus 4 sigma cos theta by rho gt. Expression for capillary rise in two parallel plate. So H is equal to say 2 sigma cos theta by rho gt, where t is the distance between two parallel plates. Expression for capillary rise in annular. So H is equal to say 4 sigma cos theta upon rho g t outer minus t inner. Now ninth property is pressure. It is a normal force exerted by a fluid per unit area. Its SI unit is Newton per meter square and its dimension is m L the power minus 1 t the power minus 2. And tenth property is temperature. It is a measure of hotness and coldness of system. In thermodynamic sense, it is measure of internal energy of a system. 11th property is thermal conductivity K. It is related the rate of heat flow per unit area to the temperature gradient, and its SI unit is watt per meter Kelvin, and its dimension is m L t the power minus 3 and theta the power minus 1. 12th property is specific heats. It is the amount of energy required for a unit mass of fluid for unit rise in temperature. And last property is speed of sound. An important consequences of compressing a fluid is that disturbance is introduced at some point in the fluid. So propagation at infinite velocity. The velocity at which this disturbance propagates is known as acoustic velocity or speed of sound. That's all for today's lecture. We have completed all the properties of fluid, and next lecture we will complete the pressure and measurement. Hope you like the video. Please comment, share and subscribe. Thank you. Hello friend, welcome to my